Yeah, so we defined this group. Now I want to show you that this is isomorphic to what we had before. So K1 of lambda G S star is isomorphic to K1 of what we denoted there by lambda G M H of G. So let me sketch a proof. Okay, so how does one, what's the, I'll define two maps. I'll not check that they are well defined. So modulo well definedness, it will be obvious that the composition is identity. So what's the map in this direction? So this is represented by, so any element is represented, it's generated by this. So you can take the generator to be C dot A, where A is an isomorphism from determinant of 0 to determinant of C. And now C is, so we just do as before. C is a cyclic when tensored with lambda G S star. So that gives an, so you just tensor the whole thing with lambda G S star. This gives an isomorphism between this and a cyclic object, which is, and so this is canonically isomorphic to determinant of 0. So it gives you an element in K1 of lambda G S star. So we just have to check that this is well defined. So if you have this relations, then you also obtain the relations in the image. So I won't do that. Now the other way around, so again this is, we have seen something like this before. So you have K1 of lambda G to MHG. So take any A in here. Let A in some large enough GLN lambda G S star represent A. And again you write A as B inverse C, where B and C are in Mn of lambda G intersection GLN lambda G S star. You send A to lambda G to the N comma identity. So I'll say what identity means here, into lambda G to the N B lambda G to the N identity and inverse of this. So I'm writing this group multiplicatively. Okay. So what does identity mean? Identity, so this is the identity canonical homomorphism from lambda G lambda G to the N to determinant over lambda G of lambda G to the N. So so this gives you an isomorphism between determinant of 0 and determinant of this complex. So determinant of this complex. So and similarly for that. So this determinant is not determinant of C. Okay. So this gives you a map in the other direction. So the two are, the composition is obviously identity, and just have to check well definedness, which I won't do here. Okay. Now let me just briefly recall describe the localization sequence with this group instead of k1 of lambda g s. So the nice thing about this new description of k1 is it's in terms of exactly the objects that we are interested in. So localization sequence becomes, so you have k1 of lambda g to k1 of to k0 mh of g. So we have to put this one in here. Now what's the map? So the map is from here to, so if a is represented by a, then this just goes to lambda g to the n a lambda g to the n and identity. So this is acyclic, so it remains acyclic after localizing because localization is flat. And what's the map from here to there? You just take any C and A and send it to the class of C. Okay. So what we wanted to do was show that this the 5-author main conjecture implies Fukaya-Kato main conjecture. And so the 5-author main conjecture says that there exists a periodic L function in k1 of lambda g s star. So with correct interpolation, so the delta of C is minus of C of f infinity over f, and correct interpolation. Now you just take the Z to be, so Z is equal determinant, isomorphism between determinant of 0 and determinant of C of f infinity over f. So take this to be image of theta in this k1. Okay. Now all one has to verify is that the interpolation doesn't change. So, but I won't do that. So the main thing that I want to do now is to say how the topological description of the topological construction of K theory makes this new description of K1 more transparent. Okay. So before that, let me just make a remark that the above description is not special to K1. So above description of K1 can be used to describe K1 of lambda g as well. So you just, instead of taking the category mh of g, so replace mh of g by the category of all acyclic perfect complexes of lambda g modules. So basically, instead of using the set S, I'm just sort of not taking S2. I'm just taking S to be all the units, something like that. So there was nothing special about S. We could have taken any S where we can localize. So we may not localize as well. And so you just take all the acyclic complexes. So this is, I just made this remark because sort of this may look surprising, because K1 of lambda g is also given by K1 of, maybe I shouldn't say also, it's given by K1 of the category of perfect complexes of lambda g modules. And we are taking just acyclic, so it may seem like a much smaller thing we are taking, but it gives the same K1. That's because firstly the relations, the generators and relations, if we take this category, would be different, and secondly because it's a nice category, so we can sort of get away with taking something very small. What do I mean by nice? Okay, I'll say what do I mean by nice in a few minutes. Okay, so now let me describe. So I won't do description of, I won't give the construction of Waldhausen of the K-theory space, because it's very sort of technical and complicated and not very illuminating. So I would just say what kind of topological space we get. So just take the sort of relevant properties of the topological space, because whatever I'm going to say is very, very speculative anyway, so I'll not sort of go through the whole technical construction. So let R be any ring and CPR be the category of perfect complexes of R modules. Okay. Then CPR is has a structure of okay, let me see, can be made into Waldhausen category by, so for Waldhausen category we need two things. So we need three things. So 0 is the zero object. Okay, so we need a zero object. So just take the complex of all zeros, so that's the zero object. Secondly, we need a cofibration. So what are the cofibrations here? So you take the complex A into B, so this is if AI to BI is injective and co-kernel is projective. Projective R module. Okay, so just monomorphisms like these will be called cofibrations. So, and then the third thing is we need weak equivalences. So A to B is a weak equivalence if it is a quasi-isomorphism. meaning that it induces isomorphism on cohomologies. So
perfect complex now means that they are themselves projective, or
yeah, projective.
Yeah, all the terms are projective.
Yes, so perfect complex means bounded complex of finitely generated projective modules. Okay. So any category with these three things and then satisfying certain list of axioms is a Waldhausen category, and sort of we are only interested in such a in this example of the Waldhausen category. So what can we do? Sorry, this is one example, and then the other example that we are interested is in the category MHG. Sitting in, okay, so sitting in as a full subcategory of lambda G. Okay. So let's see. So to a Waldhausen category C, we can attach a topological space, let me call it L of C, such that so pointed topological space, so 0 will be there, such that any object in C gives a point in this space L of C, and any weak equivalence so A to B, this is a weak equivalence, gives a path from the point A to the point B. So this is sort of mainly what we are interested in, but and then so what we do is we define Ki of C to be pi I of this topological space L of C. Okay.
This does not characterize the space.
No, this does not characterize. Yes, right. But yeah, I mean, I don't know any properties sort of that characterize it abstractly, so I have to either give a construction or sort of say that this is the only thing that we need out of it. Right? So yeah, I'm sorry. So this obviously does not characterize it. But I would take this as a sort of black box, the existence of such a canonical topological space.
I mean, also it doesn't make sense in the current context to say it characterizes it, because there's no other definition of Ki.
That's what I said. I don't know any sort of abstract characterization of this topological space. Of course, if you know what ki's of a category are, then it would characterize it as long as you want this to be functorial in some sense. So yeah. So I mean, I can sort of go ahead and give the construction of this topological space from a category, or I can just sort of assume that such a topological space exists and this is what we need from it. Okay. So
In this generality, I mean,
Yeah, the objects in the calculus.
that's what he said is, or if you start from arbitrary output.
yeah, so you can just define k0 in elementary terms by
Oh,
taking.
you mean if you start
Yeah.
from that category?
No,
then
if you start from that category, you can define k0, k1. You can obviously for a ring you can define all
Well,
minimal
that's
k.
not the most general well-known category.
Yeah. So you can just define k0 and then, but that won't characterize the topological space, of course. So yeah.
Of course, yeah, it is a theorem that this is correct. This is that's what
Yes. So I'm sorry, I know this is sort of very unsatisfactory, but I don't want to go into the technical details of sort of how to construct this thing. So, but if we assume that there is a nice construction of this K-theory space, then so what this does is sort of for CPR we can think of determinants as follows. So, so you have this Waldhausen category, and you just take the okay. So you have this, and you just take the quasi isomorphisms, and from this you you get determinants. So how do you get this? So so the determinant category so this is the Picard category, right? So has objects the isomorphism. Let's see. Right. So objects. So objects of this category are objects of CPR and morphisms between any two object is paths from A to B up to homotopy. Okay. And this CPR is so constructed that K1 of so that pi 1 of this L CPR is equal to K1 of R. So the K1 defined before. Okay. So what does this say? This says that morphisms between A and B is either empty or a K1 torsor. Because we know, so if A is equal to B, then you just have a loop set based at any point, and if A is sort of then and then we know that paths from one point to another is, if there is a path, then it's a pi1 torsor. Okay, so here I'm of course taking the base point to be 0, but yeah.
But you had another determinant category before, so it's slightly.
Yeah, so I'll say what this is. So, so this is how, I mean, for exact categories, this is how Deligne constructs his determinant category. So he takes objects and he takes he works with the, so for exact categories, Deligne works with, so for exact category A, Deligne works with this this equivalence topological space BQA, and then the L above would be like would be the loop space of BQ. So it is denoted by this thing. Okay. So I'm just sort of trying to think of objects of the category as points and determinant as paths between them, rather than so what Deligne has is objects are like loops, and then determinants are homotopies between the loops. So I'm just taking the loop space just to, because I'm not giving the construction anyway, so I can sort of take the loop space just to make the intuitive picture clearer. But the remark I should make here is the following. So so how is L constructed? So so from a Waldhausen category, one gets what is usually called this WSC, and then and then one gets a geometric realization of that. So from any category to sort of, there is a standard procedure of getting geometric realization of a small category, and sort of you have to do that process twice actually. So from here to here and then there, and then L above is actually the loop space of this geometric realization. But there is no categorical model for this loop space directly. So meaning that there is no category which gives you, by applying the standard recipe of getting a topological space out of category, there is no category which sort of, we don't know any category which gives you the loop space directly. And this is sort of all the problem in all the complications in describing the K1. So this makes describing even K1 of a Waldhausen category in terms of generators and relations very difficult. So if you could construct a categorical model for this loop space directly, then it would be sort of, describing K1 would be possible, I think, at least. Okay. Sorry. So no, but the only thing that we want to take from this vague description is that points objects give you point, and determinant is like a loop. Sorry, a determinant from one of isomorphism from one object to another gives you a determinant which is like a path from that point to the other point. Okay. Right. And this construction is functorial in the sense that an exact functor f from one Waldhausen category to another. So by exact functor I mean which is exact in the usual sense, and which sort of carries the Waldhausen structure from the category C to D, gives a continuous map LF from LC to LD, and hence maps on KI. I don't want to spend too much time on the technical details here, because what I'm going to say is sort of very speculative, so I don't know how much, how much interest people will have. So, okay, so with this description, K1 of lambda G or K1 of lambda G S star is the group of loops at 0 up to homotopy. Okay, so this is sort of what we have to take out of the construction. So this is loops up to homotopy. Now okay, now if we have a path from determinant of the 0 object, but this is over lambda G, to determinant of the object A, where A is in MH of G, then this path becomes a loop under the map L of lambda G. So yeah, this is CP. So localization is an exact sequence. So we get a continuous map like this into the localized thing, and then under this map, this path from 0 to A, it becomes a loop, because A itself becomes 0. Okay, and then one can show that conversely any any acyclic complex over lambda g s star can be obtained by localizing a complex in MH of G. So, so any loop here should come from a path like this. Conversely, any acyclic complex of lambda g star modules can be obtained by considering some complex in MH of G with lambda G S star. Okay. So this shows that any loop can be obtained as a path, and so it is natural to expect the description of K1 of lambda G S star given by Fukaya and Kato. I think this is, so it's quite reasonable to expect such a description. Okay. Now, so the question is, how do we sort of extend the so I want to make a few sort of comments on few speculations about extending the conjecture of Fukaya and Kato to the higher K group. So the K theory localization sequence extends to the left as so we have K2 of lambda G S star, and then we have this K1 of this category MH of G, which goes to K1 of lambda G, which goes to K1 of lambda G S star. So before I just wrote down this part of the thing, and this goes to K0 and so on, but we know that this is surjective, so I'll just stop here. Okay, so now Fukaya Kato says that there exists a canonical path up to homotopy. Okay. From the point determinant over lambda G of 0 to determinant lambda G of this complex C that we are interested in, okay, the Selmer complex. Now what happens if we choose two different paths in the same homotopy class? So let gamma 1 and gamma 2 be two representatives of this path, okay, be two representatives of this path. So I'm just so something like gamma 1, gamma 2 inverse, or gamma 2 inverse gamma 1 is a loop at 0, and it's sort of and is homotopic to the trivial loop. So I have determinant of 0 here, and then I have determinant of C. Now I choose two paths which lie in the same homotopic class. So if I take one and come back with the other, it should have it should be a trivial loop around 0. So okay, so gamma 2 inverse gamma 1, so it's a loop around 0. So that gives a class in K0 K1 of MH of G, because all these objects are in MH of G, so it gives you a class in and it's a loop around 0, so it gives you a class in MH of G. Okay. And its image in K1 of lambda G is trivial, because that's what this means. So the question is, what does image, sorry, what does an element in K2 of lambda G S star referring to gamma 2 inverse gamma 1 tell us about our original complex that we had. So this is sort of so it's clear what it means. So so this element in K2 is choosing a homotopy from gamma 2 inverse gamma 1 to the trivial loop. So the question is, what arithmetic information does this have? Okay. So I have no answer to this question, obviously, but what the generalization of this conjecture, if there exists one, should be that there is a, okay, so in K1 it was that there is a path which sort of which is determined by L values. So the question is, are there so yeah, I mean the question formulated in different ways, are there interesting arithmetic invariants in K2 which determine this homotopy. Okay. So this is sort of what I wanted to explain, and so I don't want to go into much detail, but this could be sort of one of the way of generalizing the conjecture of Foucault and Kato, and this already appears in a very abstract sort of language. It appears in thesis of Martevites in his so it was Freiburg. Okay.
To make this question slightly more precise, you have to say what gamma 1 and gamma 2 would be. You have to be in a situation where you have two different paths.
Well, I mean, so we are taking sort of paths up to homotopy. So I'm taking two paths, and I'm taking an explicit representative of a path.
Right, but Foucault and Kato's conjecture in some sense gives you a way to construct one homotopy class, right?
One homotopy, but now I'm taking two different paths in the same homotopy class.
Right, but for this question to have a reasonable answer, it would be when you have two different ways of using MO to pass inside the homotopy class, right? So you wouldn't expect a nice answer for an arbitrary choices of MO.
Right.
So this is the situation where you have a mixed mode.
Yeah. So I mean, I'm leaving that one vague as well. So what choices would be the nice ones? I don't know. Okay. So, but then I want to sort of take another, because I'm making some speculations. I want to take another guess at. So if one tries to describe it like this, then I think it's natural to, then it may be natural to sort of describe K1 of MH of G by the following generators and relations. So generators are given by triples A, A1, A2, where A1 is a isomorphism from determinant of, so AI is, so we have two different isomorphisms, and then relations. So this may be very wrong, so just this is 1 for when the two are equal. So you are just taking the same path and coming back in some sense, and then A1, A2 into B, B1, B2 should be same as A direction B, A1 into A2, and A1 into B1 and A2 into B2. Okay, and the map from K1 of MH of G to K1 of lambda G is given by, so I have determinant of 0 to determinant of A, this is A1, and then this goes to determinant of 0 by A2 inverse. So this gives me A2 inverse A1 gives me an element in K1 of lambda G. So this is, so there are three questions that I want to end with, and I'm sorry for such a vague talk. So next time I'll be very concrete, and I'll tell you a strategy of proving the conjecture of this main conjecture in the 5 author paper for totally real fields, and I'll show how the proof works in some cases. So it will be very concrete and sort of all no speculations there, or very minimal. Okay, thank you.